Good morning, everyone. I welcome you all to our next day, the next day of our workshop. Our first session is opened with a talk by Alexander Karpov. I just remind you that we have 40 minutes, including questions, so please leave like 5 minutes or so for them in the end. So, Alexander, the floor is yours. Please start.
Okay, thank you. Yesterday, we began with Arkady Slinko talk about condensed domains. There is a variety of condensed domains, and SinglePeaked Domain is only one of different possibilities. And SinglePeaked Domain is characterized by never bottom condition. So for each triple, we have at least one alternative, which is never at the end of preference order in each triple. And now we will go deeply inside SinglePeaked Domain. So what do we have? Sorry. In general, in economics and computer science, there is a general topic of structural preferences. So we have some structured alternative space, and this structured alternative space leads to structured preference profiles. There are several variants of this alternative space, and the most influential example of such structure is a line on which we put all alternatives and agents' ideal points. This line implies only order, but not a distance between alternatives. And we will have some possibilities, not unique preference order. And such possibilities are restricted by the following condition. Alternatives which are further from the agent's ideal point are worse for the agent. And I will talk about several SinglePeaked domains. So the main SinglePeaked domain is SinglePeaked on a line. Error SinglePeaked, it is SinglePeaked on each triple of alternatives. SinglePeaked on a circle. So we have the same conditions, the further the worse, but on a circle. The restricted tier domain is a special domain. It's which arises in random assignment problem recently. And the Fishbone Domain, it is, I will show that it is also SinglePeaked on a circle. It's a subdomain of SinglePeaked on a circle. So let's start from SinglePeaked preferences. I think that all of you knows definition, but so just reminds us. So we have a finite set of m alternatives and finite set of n agent. A set of preference order is called a domain of preference order. And when we talk about a preference profile, it is a multiset where some preference order are repeated. So we have domain is a set of different preference order, and a preference profile is a multiset with some repetition of preference order. Each domain of SinglePeaked preferences is defined by an axis. This axis is a linear order over X, and preference profile is SinglePeaked with respect to this axis if each agent upper counter sets are connected according to this axis. So in some sense, it is convexity condition. So we have a line, and each upper counter set of each agent is an interval of this line. So we prefer our top alternative is 1. Our two top alternatives is two neighbor neighboring alternatives, 3 top alternatives is interval, and so on. So we define SinglePeaked preferences in such way. And we want the main task is to find exact number of SinglePeaked preference profiles. What is the problem? We have a high number of axes, so m factorial divided by 2 different axes and different corresponding domains. Some of these domains have non-trivial intersections. So some preference profiles are attributed to several axes. For example, if we have purely homogeneous preference profiles with exactly one type of preference order, then these preference profiles can be attributed to several axes, surely. And because this structure of intersections is non-trivial, the problem is highly difficult. So Durant in 2003 found the number of SinglePeaked preference profiles for 3 and 4 alternatives. So here we have a small number of domains, and we can manually find all intersections. Lackner and Lackner found the number of SinglePeaked preference profiles with 2 agents. So with 2 agents, it is permutation. So if we fixed the first preference order, the second preference order is a permutation restricted by some pattern, and we know this pattern, we know how to restrict this permutation, and from combinatorial literature we know the number of such permutations. And I solved this problem for 5 alternatives recently by considering all domains and all intersections. Here I will show the solution for general problem, finding a recursive formula for the number of preference profiles. So to do this, I want to define normal SinglePeaked domains and normal SinglePeaked preference profiles. These domains are the definition is the following. So if the order 1, 2, 3, etc. m belongs to the domain, this domain is normal. If the first preference order of a preference profile is 1 to 3, so on m, then this preference profile is normal. So I consider only domains and preference profiles with order 1, 2, 3, 4, so m. And there are 2 powered m minus 2 normal preference domain, SinglePeaked domains and normal axes. And here I present a special order of these axes. So each normal axis, in each normal axis sets 1 to k for intervals according to the axis. So we know that order 1, 2, 3, 4 m belongs to this domain. Because of this, we have interval 1, 2, interval 1, 2, 3, interval 1, 2, 3, 4, and so on. And so we add additional k, and there are 2 possibilities to add k: consecutive order and separated. So it's possible to add 3 as 1 through 3. So we have 3 in consecutive way, or we have 2, 1, 3. So 2 and 3 are separated. So we have such binary representation of normal axis in increasing order. So the order is important because we can further unite this axis in parts in the following way. So also example with 5 alternatives. What is common for these 2 domains and these 2 single axes? So we have here, let us consider the first axis. If a preference order starts from 3, then this agent prefers 2 to 1. In the second axis, second domain, all preference order which starts from 3 have 1 is better than 2. So there is no preference order which starts from 3, 4, and 5 in intersection of this or the first 2 domains. But if we consider preference order which starts from 1 or 2, all these preference orders belong to both domains, the first and the second. So in intersection of the first 2 domains, we have only domains which starts from 1, 2, and the number of such domains is the number of normal SinglePeaked domains with 2 alternatives. And then we have the only way to construct a residual preference order, so 3, 4, 5. The second pair, we have the same subdomain 1, 2, 2, 1, but there are 3 possibilities to construct a residual order. So we can have 3, 4, 5, or 4, 3, 5, or 4, 5, 3. So we have subdomain, which is common, and we have common residual. And these possibilities to choose subdomain and residual are independent, and we multiply this. So we have on this column, we subtract the number of preference profiles which are common for corresponding domains. Then we should find a common preference profiles for group of domains. So let's consider the first group and the second group. We have common preference subprofile on 3 alternatives. So here we have 1, 2, 3, 2, 1, 3, and here we have 1, 2, 3, 2, 1, 3, but reversed. We know that the reversed axis leads to the same domain as the direct ordered axis. So all preference orders which starts from 1 to 3, so from domain with alternatives 1 to 3 are common for these 2 groups of domains, and there is no other preference profiles which started, preference orders which started from alternatives 4 and 5. So we have such structure of intersections, and having this structure of intersections, we get the general formula. So the number of normal preference profiles of SinglePeaked preferences equals to this recursive formula. So it depends on the number of normal SinglePeaked preference profiles with the lower number of alternatives. And to find the whole number of preference profiles, we need to multiply by m factorial. It's the number of possibilities to define the first preference order. So for a small number of alternatives, we have such formulas. So in these formulas, we have not only minus, but also plus. So there is a big number of members in this sum. And so for approximation, for some probability calculation, of course, it's enough to calculate only the first member. So because the base of this power sum diminished quite quickly. So if we want to calculate approximate number of SinglePeaked preferences, we need only the first member, but the general number is interesting for combinatorial reasons. And what is interesting is to find a way to generate uniformly SinglePeaked preferences. So up to date, we have only algorithm how to generate SinglePeaked preference profiles with given axis. Having precise number of SinglePeaked preference profiles, we can get conditional probabilities of special types of SinglePeaked preference profiles, and we can have we can construct an algorithm, also iterative algorithm of uniform random generation of SinglePeaked preference profile. So starting from small to alternative preference profiles, we can construct 3 alternative preference profiles, 4 alternatives, and so on. So using this structure of intersections, we can find corresponding conditional probabilities and get uniform distribution over all SinglePeaked preference profiles. Another special case of SinglePeaked preferences is narcissistic preference profiles. It's a profiles where each agent has own special top alternatives. So alternative J is the most preferred alternative for agent J. And for this preference profiles, so we have simple formula. So we have the number of SinglePeaked narcissistic, normal SinglePeaked narcissistic preference profiles is this product, and general SinglePeaked narcissistic preference profiles is the same number multiplied by m-1 factorial. It is a number of possibilities to define the first preference order, starting from 1, then m-1 possibilities to define the first order. SinglePeaked on a circle. So we have another structure of alternative space, not line, but a circle, but the same idea is that upper counter sets are interval of a circle permutation. A SinglePeaked on a circle is not condensed domain, so we have condensed cycles inside it, and it is symmetric. So we have, in some sense, SinglePeaked and single-dipped together. And this domain is invariant to rotating and flipping a circle. So we have m-1 factorial divided by 2 maximal SinglePeaked on a circle domain. And all domains are in some sense the same, so are isomorphic with each other. And in each SinglePeaked on a circle domain, we have m multiplied by 2 power 10-2 preference order. So it is approximately m times bigger than SinglePeaked domain. So, and in this case, we can order not access, not permutation, but so-called permutation in the same way. And so here we have normal single-peaked on a circle domains. So normal means that these domains include order 1, 2, 3, etc. And we have the same structure of intersections. And in intersection, we have also normal single-peaked number of normal single-peaked preference profiles. So we start from 1, 2, and we have here 16 possibilities to define a residual order. So we can go to the left or to the right. So we can, after 1, 2, we can add 3 or 6. So it is so-called permutation. Then we have, for example, 3, then either 4 or 6, and so on. And this structure of intersections of number of sets of preference profiles leads to this formula of the number of single-peaked preference profiles. So it's close to, looks like the previous formula. And for a small number of alternatives, we have such numbers. So we have even bigger difference between the base of the first member and the second. So approximation by the first member is quite good here. So we can use for example, probability calculation only the first approximation. Error single-peaked. It is a more general class than single-peaked domains. It is condensate domains, which is characterized by single-peaked condition for each triple. So for each triple, we have single-peaked domain, but in general, this domain can be not single-peaked. For example, for 4 alternatives, we have single-peaked, and the second domain is the following. So you can see that this domain does not include the reverse of natural order of 1, 2, 3, 4. So only single-peaked domain has reversed or two reversed order. All others, single-peaked domains, have no pair of reversed order. So by computer, I find all intersections of 8 normal domains and obtain this very formula. For 5 alternatives, there are 6 error single-peaked domain, and providing some computer calculations, I found all normal single-peaked domains, and then there are 64 normal single-peaked domains. Then I unite these domains in some groups. Then I found computational intersections of these domains inside groups, and then intersections between groups. So then I get this formula. We will see that this number includes more members in the sum than simple single-peaked domains. So, and up to now, I have no ideas how to generalize this formula. So maybe there is some recursion, but still it is the last result for every single-peaked domain. So we have only the number for 5 alternatives. Restricted tier preferences. I think that this notion is new for you. So a domain is restricted tier if there is another partition of alternatives such that the cardinality of each part does not exceed 2. So we have only parts with 1 alternatives and 2 alternatives, and each voter each voter's preference order respects this weak order. So within this each group of two alternatives, the order can be arbitrary, but the order between groups is the same for all orders. And for free alternatives, we have domains 1, 2, 3, and 2, 1, 3. So we have group 1, 2, and group 3. And all orders respect the weak order. So we have 1, 2 is better than 3. But there is no restriction on order between 1 and 2. And the second ability to define restricted tier domain is 1, 2, 3 and 1, 3, 2. So these domains are maximal restricted tier, but of course these domains are not maximal condensed domains. Why these domains are important? So we have a paper, Liu and Zheng. They proved that under the restricted tier domain, the probabilistic shared rule is uniquely characterized by strategy proofness, efficiency, and equal treatment of equals. So these domains arises not in voting theory, but in a random assignment problem. So there is no, so the problem about Condorcet cycle and Condorcet paradox is not relevant here. Also, in some case relevant, but not so important as in voting theory. And because of this, it's not important either this domain is maximal Condorcet domain or not. And we can consider this restricted tier preferences. It is interesting that restricted tier domains is simultaneously group separable, so it can be divided by groups and single-peaked. So it's also single-peaked domain, and here I have found the number of single-peaked preference profiles. So we have easy structure and easy formula. I do not want to show the proof. It's quite easy. And here there is a forbidden configuration characterization of restricted tier domain. A preference profile is restricted tier if and only if there is no two distinct agents and three distinct alternatives such that. So we have normal order ABC, and either the third alternatives became the first, or the first alternatives becomes the last. So this configuration corresponds to permutation pattern which avoids patterns 2, 3, 1. So the first is the last, and 2, 3, 1, and 3, 1, 2. Such permutation are called free permutation and are counted by Fibonacci numbers. So we have quite easy combinatorics for this, and it's quite easy formula for preference profiles. Fishbone domain. Yesterday, Arkady Slinko already defined Fishbone domain, and here I repeat this definition. So a domain is called the Fishbone domain if it satisfies the alternating scheme. There exists a linear ordering of alternatives, A1, AN. So, and it's important to have numbers from 1 to m, such that for each triple of alternatives of indices I, j, k, the restriction of the domain on the sets on this set AI, A, j, k is single-peaked if j is even and single-dipped if j is odd. And there is possible to define another domain where single-peaked if g is even is odd, sorry, and single-dip if g is even. And there are examples for 3 and 4 alternatives. And what do we get for the Fishbone domain? Accidentally, the Fishbone domain is a subset of the Spock domain. So the Fishbone domain is single-peaked in a circle. So we have this order A1, AM, and we can put these alternatives on a circle in a special way, and then show that the Fishbone domain is a subset of single-peaked in a circle domain. So in some sense, it is the largest condensate domain inside single-peaked in a circle domain. So single-peaked in a circle domain has nice properties computationally, and so there are some algorithms how to apply properties of single-peaked in a circle domain to different computational social choice problem. So there is a paper by Lackner and Peters. But the main problem for a single-peaked in a circle domain is that this domain is not condensate domain. And here I show that the Fishbone domain is a subset of single-peaked in a circle domain, and we can apply all results, all algorithmic results from Lackner and Peters for the Fishbone domain. Another interesting result that there is no forbidden configurations characterization for the Fishbone preference profiles. So we know that there is Harringer-Ballester characterization for single-peaked domain. We have Peters and Lackner characterization for single-peaked on a circle domain, but Fishbone domain has no such characterization, neither finite nor infinite. So we can detect, but algorithmically, even without this characterization, we can detect Fishbone domain. So we can think about constructed single-peaked on a circle domain, firstly, and if this preference profiles is single-peaked on a circle, then after that we can think either this domain, either this preference profile is Fishbone or not. So conclusion. The obtained formulas can be utilized for probability calculation under impartial culture assumption and with minor change under impartial anonymous culture assumption. The obtained structure of intersection, firstly for single-peaked domain, can be utilized for random sampling of single-peak preferences. Such sampling procedure would be iterative, so we will start from two alternatives, and we know the structure of intersection. We will construct 3 alternatives preference profiles and 4 alternatives preference profiles, and so on. So now we know all conditional probabilities from this iterative formula, and we can find this. We can get uniform random sampling. Open questions. So for error single-peak domains, we have results only for 5 alternatives, and we do not know the number of error single-peak domains. And the second problem is the number of Fishbone's preference profiles. So Fishbone domain is the largest domain which we consider now, and it is interesting what is the number of preference profiles which belongs to the largest condensate domain within this set of domains which are close to single-peak domain. That's all. Thank you for your attention. So we have time for questions.
Thank you, Alexander. I have one quick question about this impressive recursive formula for the number of single-peak domains.
preference properties.
It's almost reflectorial when I see something like that to try writing down a generating function, maybe a differential equation for generating function, or maybe some equation with convolutions. I guess you've tried doing that, right?
Yes, yes. Convolutions
does it
here.
work?
Does not also, I don't know, maybe there is some special features and special, I don't know, results which I don't know, but a simple technique does not work.
So it's unclear to which special function it corresponds, because it's very intriguing. I guess the problem comes from this binomial coefficient that is that goes to the power n-1, right?
Yes, yes. So without this coefficient,
it's
it would
the problematic
be,
part.
It would be. There is no problem.
Thanks. Any questions from our from our offline participants?
Yes, thank you for the talk. Very interesting indeed. I mean, I have a question, a sort of a clarifying question with respect to your statement, your proposition that something like the Fishbone domain cannot be characterized by a test of the sort for every triple or every quadruple of. So, yes. Does this sort of statement also includes the elementary algorithm that you can do for a regular single peaked on a line, you know, the simple exercise where you say, okay, I give you a profile of preferences and I want to recognize if there is a way to arrange my alternatives such that this profile is single peaked. So instead of going through all the triples, you just say, okay, what are the last alternatives of everybody? If it's more than 2, we know already it's out. If it's 2, we may continue. And then we have new conditions on the next 2 last alternatives and so on and so forth. I mean, so this sort of algorithm is, I guess, not finite because if you have, if n grows large, I mean, it could take a long time. But is there something similar that can be done for either the single peaked on the circle, the Fishbone? I mean, single peaked on the circle and Fishbone are really interesting, right? I mean, because one is not a Condorcet domain, but it's very natural. And the Fishbone is intriguing and is a Condorcet domain, right? I mean, I'm not wrong there. So it's I really like this proposition where the Fishbone is actually a subset of that. I mean, is it a difficult proposition? The first one, the Fishbone domain, is a subset of single peaked.
The first one is more difficult than the second.
I see.
Second proposition. So, for example, for 4 alternatives, we have 4 alternative single peak domain is forbidden configuration for the case of 4 alternatives. But 4 alternative single peak domain is not forbidden in general case. If we have, for example, 8 alternatives and there are 8 even numbers, and a restriction to these 4 even numbers is single peaked. So for small domains, this configuration is forbidden. For big domains, is not forbidden. And in such way, we have the same configuration with simultaneously forbidden and not forbidden.
I see. Okay.
Therefore, the Fishbone domain is a subset is quite tricky. So,
what happened?
So it's not is the first proposition is not simple so the proof. So I consider forbidden configuration characterization from Lackner and Peters and show that the Fishbone domain avoids all configurations, all 3 configurations. So it's not possible to define an ordering of the Firstborn domain if we have these configurations. So I applied Lackner and Peter's result about forbidden configurations.
Okay, thank you. Thank you.
Thank you, Alexander. Maybe we have time for one short question from our online participants.